be a quick technical overview of the TwoStack Layer 1 token. You might have heard me in various places talk about this thing. TSL1, right? TwoStack Layer 1 token. What is it? How does it work? Well, let's draw a couple of transactions first so you can get the general gist of it. Basically, the way that it works is like this, in broad strokes. This represents one token. These two transactions, transaction 1 and witness 1, together these represent a token. Or rather, this represents the witness to a token, and then this is actually the token. There will be some outputs attached here, and then there will be some inputs over here which spend, and then there's one output here. And then of course, if you were to transfer the token, it would look something like this, right? You would transfer to T2, and then T2 would by itself have its own witness, and the witness here again will have inputs, and the token in its new incarnation will have outputs. The token over here will have inputs. It will have a funding input. It will have an input that spins from the witness, and it will have an input that spins from this out point over here in T2. Now, I'm going to call this one, for the sake of clarity, SHA-256. I'm going to call this one, for want of a better term, plug point 2. I'm going to call this one, for want of a better term, plug point 1. And this one over here, this output here, I'm going to call, this is going to be the change output. Then this is going to be the change input, sorry, the funding input, right? So this is, can't write now. This is funding, okay, and then this here will spend from there. This here will spend from there. So I'm just going to say that this is the P1 spend, and this is the P2 spend, and we'll come back to this. And then this is funding input. Right, this is just how we fund the transaction, and then this guy here spends from there, and this guy over here spends from here. Now, the thing to note here is what actually happens in all of this in order to make sure that this representation over here, that this essentially needs to have the following properties, right? The first property is that it is fully minor validated, yeah. And then the second property it needs to have is that it is tamper evident. Right, so we're not going for tamper proof, we're going for tamper evident, meaning that it is very easy to detect that somebody has messed with it, because it's a bit harder to enforce completely that somebody can't tamper with it. It is still possible to copy all of these outputs, for example, into a new transaction, but then it should become immediately obvious what is going on when the person tries to, for example, spend this new token over here. This witness will break, for example, right? That it becomes tamper evident when somebody tries to do anything funky with it. The third property that this token has is no indexers are required, so it doesn't require any indexing. And then the fourth property is no transaction growth. Right? These are all very important properties for a token to have. Now I'm going to slowly erase all of these things because it's my first time in a long time using this tool. I guess I could do this. Let's see. Boom, done. Now do I get back my tool for drawing on this board? Come on. Where's my drawing tool? Okay, now I've gone and done it, haven't I? Drawing tool. Nope. Drawing tool. Scribble, scribble. Nope, that's not it. Scribble, scribble. Nope. Still not it. Which one is my drawing tool? That's straight lines. Oh dear Lord. I'm going to have to cut out this bit. How do I just get my drawing tool back? No, no. Finally. Okay. All right. Okay. So basically, now that you have an idea of how this token generally fits together, or rather what the properties of this token are, or what we are striving to do, let's talk about how we actually go about achieving those properties, right? The first one that I want you to know about is what actually happens at P1. When P1 spins plug point 1 or PP1 output, what is it actually doing? Well, it is doing a push. Oh, lost my cursor again. Lost it again. Come on. Okay, this is a little bit irritating for both of us, I'm sure. Do not want text. I do want to draw a line. So can I please draw a line? Thank you. So the first thing you need to know about PP1 here, right, is that what P1 essentially does is we push, okay, this is going to sound a little weird, so I'm going to say that we push T1, but not here. Let's look over here on the right hand side, right, where we are going to replicate P1 and we're going to replicate P2, and I'm going to say disregard that I'm writing over there, and for now just assume that this is exactly the same thing. It's PP1, PP2, and SHA-256, and that all of these things relate to these outputs, okay? Okay, so P1 does a push TX. Now, what does it push? It pushes T1 into PP1. Why is it doing that? Because we want to do, if you are familiar with this technique, we're essentially trying to do an inductive proof. Now, if you don't know what an inductive proof is, you need to go and look at Xiaohui Liu's excellent article on Medium, the S-Script Medium blog, to learn about inductive proofs. I'm not going to cover it here in this talk. You just need to know what an inductive proof is, and if you don't, go learn about it. So I'm doing an inductive proof by essentially having the raw transaction for T1, pushing it from here, right? So I'm going to push T1 and then validate some things about T1. At the same time, I'm going to do an on-chain reconstruction of T2. So essentially inside the PP1, inside the PP1 script, I'm going to have the full T1 and the full T2, which is basically rebuilt on-chain and in script. I'm not going to tell you how because it's beyond the scope. Just take my word for it that I've got both T1 and T2 available here, which allows me to do an inductive proof to essentially assert the previous spending condition here. Now, this by itself is not enough, right? So this inductive proof, if you generally do an inductive proof, what tends to happen is that you are basically going to exponentially bloat the previous transaction because you're pushing a transaction of a transaction. So if you read the inductive proof medium, you will realize that this is a potential problem. The way we work around that here is that the witness transaction W1 and W2, from wherein we push those the previous, basically the parent of T2 gets pushed here, and then if T1 has a parent, the parent of T1 will get pushed here, if there is a T0 here, for example, right? With its own witness W0 over here, then we will push T0 here. But if this is the issuance transaction, then none of that happens. But let's say for the sake of argument that P1 pushes T0 and then T1 gets rebuilt in script over here. Okay, so this is the bit that does the inductive proof. And now, because we've interrupted the repetitive or recursive problem that we have with the original inductive proof published on the script medium, by having the witness over here, we've got the decoupled witness, which means that this transaction isn't actually pushing T1 as you would have seen in the inductive proof at the medium blog post, right? We are pushing it from the witness. By doing that, we get rid of this problem of inductive proofs, basically bloating the transaction exponentially with each successive token spent. Okay. Next thing that we do. So, but pushing it from W1 introduces a bit of a problem for us. The problem that it introduces is that a person can copy out these outputs, and then you wouldn't know that the inductive proof step in the previous transaction was actually performed, because even though you can perform an inductive proof over here, you don't know that this validation here was executed, because the person, you can't detect whether or not the person has actually performed this step over here, right? If the person just creates a transaction here, W1, doesn't perform these, there is no way for you to detect over here that these things were never done, which means that the previous inductive proof was never executed, so the person can actually cheat you that way. We have to sort that problem out. The way we do it is by basically inside the SHA-256 output over here, proving for ourselves that this spend here happens, right? That this spend here, this inside loop actually, there's an inside loop here that I would like to draw now. That inside loop there has to happen. So let me get a different color perhaps to see if I can make it obvious. Let's choose this color, and then there is this bit on the inside here, right, which is kind of forming a loop, right? It's this spend from here, the spend from here to the witness output, and then the witness spending from PP2. I want to make sure that the SHA-256 script here, which I'll explain in a second, actually can detect that the witness transaction here has actually spent from PP2 over here. And the way we do it is basically by enforcing a rule that basically by agreement says that the second output of T2 has to spend from the witness output, and that the witness's third input must spend from here. Now, how on earth are we going to find this out? Well, we need to essentially perform a SHA-256 hash over W1. And we do a partial SHA-256 over W1, where we only have to take the SHA-256 hash of the full pre-image of the last part, and then we take the partially computed SHA-256 of the first inputs, right? So all of the inputs and the rest of the transaction header, we take a partial SHA-256 of that. Let me change color back to dark color so that I can draw in here that we want the partial SHA-256 of that, and then we want the full pre-image of this part here. And if you are not particularly technical, I'm sure I've lost you at this point. Suffice it to say that I am able to validate that the pre-image containing the out point in this output, because there's an output here that points at my own input. So I do a push TX, which is not the push raw TX, but this is the op push TX, which is another way of saying I'm pushing the SIG hash pre-image, which is different from the push that I would do here, where I do a full T1 push, a full push of the raw T1 transaction, right? Here I'm pushing the full raw T1 transaction. Here I'm just pushing the SIG hash pre-image to here. So I push the SIG hash pre-image, which gives me access to all of the out points this guy is spending from. Now, the second out point that this guy is spending from, I'm going to say, okay, you're going to spend from a transaction, and I'm going to perform an in-script SHA-256 hash that proves to me that this second out point here is the same as this pre-image that you've provided for me here. Once I've got the proof by matching the double SHA-256 hash to calculate the transaction ID of this partial pre-image and the full tail of it, then I basically can check that the out point in the second, in the input here spends from my neighbor in myself, because I know what my own out point is. I know you didn't follow that. You might have to listen that back. Suffice it to say, I can prove that this closed circle, that this little circle on the inside, I can prove in the SHA-256 out point here that I am in fact, that I do in fact have this W1 transaction that also spins from PP2. And the rest basically is just me doing part of the inductive proofs in PP1 to make various assertions about the shape of the transaction, and then there is essentially a backwards validation that happens over here, which once again, once I can do the inductive proof, verify the previous step, right? So the inductive proof basically looks back to check, okay, is everything in here more or less aligned with my expectations, right? So I want to know that everything in here, all of these outputs, basically align with all of these outputs, and I check those when I execute this step here. And I do the same here. I want to make sure that all the outputs here are the same as all the outputs here, and I do that check over here in this. This plug point 2 here is the one I haven't talked about here. This guy here is only there to ensure that P1 and P2 must spend from the same transaction. So when I basically spend from P2, or from PP2 here, when I spend P2 here, the only thing it checks via a SIG hash pre-image here, like the same kind of op push TX here, is done over here. It only checks that the second out point, or the second input in W1, actually spends from its neighbor here. So basically, this guy checks that its neighbor there is solid. This guy there checks that its neighbor there is solid, which means that we can always be certain that all of these spends have occurred. And then over here, we can be certain that the shape, by basically checking the inductive proofs, we can check that the shape of all of these scripts on the output side has been basically preserved. And I think that I've covered everything, right? Let me quickly write them down again to make sure that I didn't leave anything out, because I'm kind of doing this on the fly. The first one, if I recall correctly, was that we want to have full minor validation, right? So these scripts are being minor validated. We want to have, I really forget now. It's been a long day, but okay, I'm going to say them out of order. We want to have no indexes. We've achieved that because this, in order to transmit these transactions as a pair, we're going to do it peer-to-peer between two mobile phones like this. There's a mobile phone, there's a mobile phone, here is the internet. They connect directly to each other using a peer-to-peer connection without any intermediaries. And basically they will, when they do the transfer from T1 to T2, basically they will do an SPV style exchange for the transaction between them, right? So we have no indexes required. This guy only needs to do the inductive proof where he checks one step back, and the token essentially propagates via these witnesses, which must be included. And the client just basically has to check that none of this stuff has been tampered with. There is one potential edge case wherein I could, for example, right, modify some of the logic in here and propagate the logic. The problem is, at some point, I'm going to have to change it back. And if I change it back, it means that the ancestor transaction here will have, let's say I want to change it back to the proper shape, which is the one that the mobile wallets will all accept as being the authoritative one. Once I change it back, like I can change it forwards, right? I can spend it forward, change it, and then make an invalid spend by, say, let's copy this out into a new transaction. Let's say we copy this out into a new transaction. If I then spend from it, no problem. But in order for me to spend, I don't have the history, so I'll have to jump through some hoops. I'll have to modify the script code. But the script code will be, the change in the script code will be detected by the mobile wallets, which will reject it as not being authentically TSL1 script code. So now I basically have to change it back. And when I change it back and I try to run it, it will check whether its ancestor is still the same. It'll notice, nope, my ancestor is not the same anymore because it got changed in the past, and then it will break, right? So there is always going to be this inductive step, basically guides us against somebody trying to be sort of dodgy with it. Okay, so minor validation, no indexers, no bloat, right? No successive transaction bloat. And how do we achieve the no bloat rule? Well, we interrupt the recursive spend with a witness. We push with the witness. We do the inductive proof. Two transactions past the parent and the grandparent get pushed, but they get pushed from this witness. And then we push from this witness over here again, right? So we first push from W1, and then we push from W2. So no bloat. There was a fourth one, which I now really forget, and I don't want to keep you any longer, but if you can, shout it out, maybe I'll hear. Haha. Okay, that is the TSL1 token, or the TwoStack Layer 1 token, which is currently under development. Have a good rest of your day.